The second law of thermodynamics tells us that heat tends to flow spontaneously from hot to cold and never in reverse. However, if work is used, then heat can be made to flow from cold to hot. Refrigerators, air conditioners, and heat pumps are devices that do exactly this. As the figure shows, these devices use work to extract heat from the cold reservoir and deposit it in the hot reservoir. Such a process is called refrigeration. This is exactly opposite the thermal process that takes place in a heat engine. Nonetheless, energy is conserved, so that the magnitude of QH is equal to the magnitude of the work plus the magnitude of QC. Moreover, if the process occurs reversibly, then the devices are ideal and known as a Carnot refrigerator, Carnot air conditioner, and Carnot heat pump. For these ideal devices, the relation in equation 15.14 applies just as it did for the Carnot engine. Let's now look at how each of these three devices operates. In a refrigerator, the interior of the unit is the cold reservoir, while the warmer exterior is the hot reservoir. As the figure illustrates, the refrigerator takes the heat from the food inside and deposits it into the kitchen, along with the energy needed to do the work of making the heat flow from cold to hot. For this reason, the outside surfaces of the refrigerator, usually the back and sides, are warm to the touch. An air conditioner is essentially a large version of the refrigerator, where the cold reservoir is the entire room and the hot reservoir is outdoors. The figure shows a window AC unit which cools a room by removing heat from the room and depositing it outside, along with the work used to make the heat flow from cold to hot. How well a refrigerator or an air conditioner works is given by its coefficient of performance. These appliances perform well when they are able to remove a large amount of heat from the cold reservoir with a relatively small amount of work. Therefore, the coefficient of performance is defined as the ratio of QC to W. Commercially available refrigerators and air conditioners have coefficients of performance in the range of 2 to 6, depending on the temperatures involved. The coefficients of performance for these real devices are less than those for ideal or Carnot refrigerators and air conditioners. In essence, refrigerators and air conditioners are a kind of heat pump, in that they pump heat uphill from the cold temperature to the hot temperature. However, the name heat pump applies to another device which is used to heat a home in the wintertime. It uses work to take heat from the cold outdoors and pump it into the home. According to conservation of energy, the heat pump deposits inside the home an amount of heat given by the following. Thus, the heat pump and the air conditioner are similar. The air conditioner refrigerates the inside of the home and heats up the outdoors, whereas the heat pump refrigerates the outdoors and heats up the inside of the home. For this reason, most heat pumps serve a dual purpose and act as a heat pump during the winter and an air conditioner during the summer. In today's energy-conscious world, heat pumps are very popular in homes. Let's see why. The figure below shows a conventional electric heater that delivers 1,000 joules of heat to a living room. In contrast, the heat pump doesn't deliver 1,000 joules of energy directly as heat to the living room, but instead uses this energy to do work in pumping heat from the outdoors into the living room. Thus, it delivers an amount of energy, QH equals W plus QC, so that the heat pump delivers more than 1,000 joules of heat. We can also specify a coefficient of performance for a heat pump. However, since the job of a heat pump is to heat, its coefficient of performance is defined as the ratio of the magnitude of the heat delivered to the house divided by the magnitude of the work required to deliver it. Commercial heat pumps have a coefficient of performance of about 3 or 4, which depends on the indoor and outdoor temperatures.